Good afternoon, everyone, and welcome to the second in our three-part CIWEM CPD accredited webinar series, where we look at how we model the impacts of climate change on global flood risk. My name is Gavin Lewis, and I'm the Head of Engineering at Fathom, and I'll be your host for the webinar today. And I would like to thank CIWEM for their assistance and guidance in the development of this three-part webinar series. I'm joined today by my scientific colleagues, Dr. Natalie Lord, who is one of our senior climate change experts, Dr. Nans Adar, one of our senior hydrologists, and Tom Collins, our lead coastal developer, who will all be available for the question and answer session at the end of our presentation. If you have any questions as we go through the session today, please drop them into the Q&A panel in your Zoom window, and we'll be going through those at the end of the presentations. We've got about 10 minutes to go through your questions, so please send them in to us. As I mentioned, this is the second webinar in our CIWEM series. The first webinar we held in October last year was an introduction to large-scale flood modelling, in which our flood specialists explored the methods, considerations and science behind global scale flood models. This webinar can be found online, and the link to the webinar will be in your chat panel shortly. So in the second webinar, we're going to discuss the processes by which climate change is transforming flooding, the use of climate models to anticipate future flood and some of the uncertainties in these models, and how to move from global climate change to local flood hazard data, together with some use cases and references for data sets and peer-reviewed papers. Before I dive into that, let me just give you a bit of an overview of Fathom. So we're formed out of the University of Bristol by two scientists who thought they could really improve the type of flood models, particularly in data-scarce areas, at a global scale. We build and develop flood models and hazard data sets, and we work across a range of markets, including insurance, financial services, governments, NGOs, and of course, engineering and the built environment. But one thing that really underpins everything we do is the science, and we are very transparent about the scientific research that we provide, which covers the methodologies and validations that we use to develop our flood maps and other hazard data sets. And all our papers are freely available on our website for you to download and review, from some of the earliest papers on 2D flood modelling to shortly our latest paper, which is going to be published imminently on climate modelling for the UK. And you can see here are the number of papers that we've got on the screen that are all available on our website. So let me hand over to Dr. Nans Adar for the first part of our presentation.
So hello, today I'll give you an overview of how climate change is transforming flood hazard, and I'll then talk about how we can use models to predict future changes in flood hazards. So a good starting point is the atmosphere. So humans are emitting large quantities of greenhouse gases into the atmosphere, and these gases are trapping heat within the atmosphere. This means that the atmosphere is warming up. And so currently, it has warmed up by about 1 degree Celsius since the pre-industrial era. And one really important implication of this when it comes to flood risk is that a warmer atmosphere can hold more moisture. So we know from the Clausius-Clapeyron relationship that every time the atmosphere warms up by 1 degree Celsius, it can hold 7% more water. And so there is more water available to fuel large rainfall events and flash floods. And we've seen an increase in extreme precipitation events. What's interesting is that we haven't seen the same increase in large river flow. And in this webinar, I will explain why this is the case. And now from coastal perspective, coastal flood risk, climate change is causing oceans to warm up and this led to thermal expansion. Higher temperatures also causing land ice to melt in regions like glaciers and Antarctica, Greenland, and this is causing sea level to rise. And in many places, it means more coastal flooding. So let's start by asking, what has already changed? Because climate change is not something that will happen in a distant future. It's already changing flood risk now. And this becomes very clear when we look at records from the last few decades. And this is a nice example. It's a paper based on about 50 years of data and about 2,000 stations, flow gauges across Europe. And they show that climate change increases European river floods, as one would expect intuitively, but also decreases European river floods. And what they're doing is that they look at the change in the mean annual discharge per decade. So basically, they look at trends. And they show that there are different regions in Europe that respond differently to climate change. One region is in blue. It's in northwestern Europe. And the blue color means it's a positive trend that flood peaks are getting larger. And they explain it by the increase in rainfall and wetter antecedent conditions. What's interesting is that there are many regions where the trend is negative, where they observed a decrease in flood peak. And this includes Southern Europe, so that's the second region. And they relate the decrease in flood peaks to a decrease in rainfall and increase in evaporation. So drier condition, drier antecedent condition leading to smaller flood peak. And the other region is Eastern Europe and Scandinavia to some extent, where there is also smaller flood peaks, and this is related to snow. And climate change causes the snowpack to become thinner and thinner, leading to smaller flood peak when it melts in the spring. So this is a study for Europe, but a similar study was published at a global scale just a few months ago. And this is, again, we're looking at trends in annual maxima for flow at the bottom and precipitation at the top. We're looking at trends per decade over 1950 to 2017, so only observations. And they're based on about 7,000 stations from Europe, Northern Africa, and some stations in Southern America and Australia. What's interesting, if you look at the bottom plot, changes in annual maximum flow, there are many, many red dots. So many locations where we find that peak flows are becoming smaller. It's true, for instance, in Eastern Europe, many red dots there. But then if you look at the top plot, you see that in the same region, we're seeing an increase in extreme rainfall. So there is a quite different response from the atmosphere and from the catchment. Overall, you can see if you look at the top plot that there are many blue dots that we're seeing an increase in extreme rainfall in most locations on this map. Now, there are many locations for which we don't have data. We don't have data or we don't have long records that would enable us to compute trends, look at changes in flow and extreme rainfall. So one could say, well, we can just assume that things will change at the Clausius-Clapeyron rate at 7% per degree Celsius. How will it work? Well, let's look at this figure. This figure looks at scaling factors for precipitation at the top, stream flow at the bottom, and look at how much they change per degree Celsius. If everything was changing at Clausius-Clapeyron rate, the color of these two maps would be dark orange, light red. And this would be 7% per degree Celsius. But we see that it's far to be the case. There are many regions on Earth where we see changes that are greater than what you would expect based on Clausius-Clapeyron, and there are changes that are smaller than this. And then for stream flow, we see that the picture looks quite different. So it's important to keep in mind that the Clausius-Clapeyron is not a good predictor everywhere, and that rainfall and flow respond quite differently to temperature increase. So when it comes to coastal flooding, obviously, the hazard is also changes. Looking at the top plot from the IPCC, we're looking at different locations. Many of them see an increase in the tidal flood frequency, and these locations are shown in red. There are some locations that show a decrease, though. What's important to keep in mind here is that a small increase in sea level can lead to a large increase in return period. And here's an example in the lower left corner of your screen. It's an example for Hawaii, and it shows that an increase of sea level of 10 centimeters can transform a 1 in 50 event in a 1 in 1 event. So really dramatically change the frequency of extreme events, which really means that it's important to capture how much sea level will rise in the future. But all the figures I've shown so far were based purely on records. So there are changes that are going on already. So what about changes that we're expecting in the future as a result of climate change? How do we anticipate them? How do we predict them? So typically, the most common approach is to use model to anticipate these future changes. And it's not a single model, it's a chain of models, and often an ensemble of models is used to capture the uncertainty in the changes. Typically, the first model in the chain would be a global model or regional model that will simulate the climate. The global model has a full spatial coverage, and the regional model will have a coverage of a smaller domain at higher spatial resolution. These models can be used in different ways. We can extract changes in extreme rainfall simulated by these models, and then look at the changes in flash flooding. Or we can extract other variables than rainfall, for instance, temperature and radiation, and use these projections to run hydrological models and simulate changes in peak flow all the way from the catchment scale to global scale. Another option is to couple a climate model to an ocean model and to look at coastal water levels. But there are a few things to keep in mind, really, when working with climate models, or any models, actually. And the first one is that no model is perfect. And so it's really important to not work with a single model, but to work with an ensemble of models to sample the uncertainty in the projections. It's also good practice to pick, when possible, the latest generation of models. For instance, for global climate models, the latest generation is CIWEM 6, and the previous generation was CIWEM 5. But even within CIWEM 6, there are different types of models. There are some high-resolution models, some low-resolution models, and the high-resolution models capture changes in extreme better, but there are fewer of them than the coarse resolution GCMs. Also important to keep in mind that bias correction will probably be necessary before the model simulation are used to, for instance, simulate flow. And actually, there are different approaches to estimate future changes, and I will run you through 3 different approaches that can be used in the next slides. So the first approach is simply to use directly GCM outputs. So here, for instance, trends over the period 1950 to 2100 are shown based on 11 models from the latest generation of models from CIWEM 6. And you see that there is a general increase in the annual maximum rainfall over the world. I mean, most regions are showing an increase in maximum rainfall, but the trend is actually quite different for maximum flow. And in this paper, they show that in many regions where there is a decrease in maximum flow, snow is one of the key drivers and counterbalance the potential increase in rainfall. So this is one approach. Another approach is to use the CIWEM 5 or 6 simulations and to run them through a hydrological model. This specific paper compares CIWEM 5 and CIWEM 6 simulations. And the focus is on the 1 in 100 year event. And in the top row, when you see a dark red color, it means that the 1 in 100 event will occur less frequently. I mean, And you see that the consistency between CMIP5 and CMIP6 is quite good. The spatial patterns are quite similar overall, although there are differences, for instance, in southeastern US. Because they're using a whole ensemble of climate models, so 11 for CMIP5 and 9 for CMIP6, they can look at the agreement among these different models. And high agreement is indicated either by a dark red or a dark blue color, depending on the change. And you see here again that there is actually quite good consistency between CMIP5 and CMIP6, maybe with slightly greater agreement among the CMIP6 model than among the CMIP5 models. Now we've talked about how things will change for a specific period by the end of the 21st century. Another way to look at change and climate change is to swap time for global warming levels. So global warming level is an increase in temperature, in global mean temperature since the pre-industrial era. And this can be used to sample different periods from climate model. And one reason to do this is that under the Paris Agreement, we're trying to keep global warming below 2 degrees and ideally below 1.5 degrees. So if we take the example of these two models, the model in green and the model in orange, you see that the model in green warms up quicker than the model in orange. The model in green exceeds the 2 degrees Celsius threshold by 2060. So one could actually select a simulation of a given length, for instance, 30 years for this period, and this would be impacts under 2 degrees of global warming. And one could do the same operation for the model in orange, but because when orange warms up a bit slower, the period would be later. It would be around 2085. So one can extract these two slices of simulation and then combine them and look at the changes that we're expecting for a warming of 2 degrees. And this is what was done by this study. They're looking at 3 different global warming levels, 1.5, 2 degrees, and 3 degrees, and they're forcing 3 hydrological models by 5 GCMs. And the patterns they're finding in the top row, looking at the changes, something quite similar that you're familiar with now, with wetter condition in the northwest and a drier, a smaller peak in around the Mediterranean Sea and Scandinavia. What's interesting here is that in the bottom row, they also compare the contribution of the global climate models and hydrological model to the total uncertainty in the projection. And you see that as the global warming level increases, the importance of the hydrological models when it comes to the total uncertainty increases. And by 3 degrees, the contribution of the hydrological model to the uncertainty is similar to that of the climate model, which really emphasizes that not only it's important to use more than one climate model, but when possible, it's important to use more than one global hydrological model or hydrological model of a specific region. So how do we then simulate inundations? Well, I saw this slide from the previous webinar. And for the previous webinar, the recommendation was to use gauging station records as an inflow hydrograph. Instead of this, one can use hydrological projections, so simulations from hydrological models driven by climate model, and by combining them with channel bathymetry and terrain data and filling them into a hydraulic model, one can actually generate a hazard map under climate change. So this is one approach, but for dataset Global 3, we've selected a different approach, and I'll let my colleague Natalie tell you about it.
Hi, everyone. Apologies, I've got a slightly unstable internet connection, which is very good timing. Thanks, Nance. So we've covered some of the theory about how floods may change in the future in response to climate change and some of the ways that this can be modelled. I'm now going to focus on some specific examples to show how we at Fathom have gone about modelling changes in future flooding on different spatial scales. So firstly, we'll have a look at Fathom's climate dynamics, which is our framework for modelling future changes in pluvial and fluvial and coastal flooding for any future scenario anywhere in the world. I'll just be giving a very brief overview of our climate dynamics framework. So if you'd like more information, please have a watch of our climate dynamics launch webinar recorded in November, the link for which will be posted in the chat. So in the first CIWEM webinar that we gave in October, sorry, we talked about some of the methods that can be used to link data from global climate models to flood models. And one of these methods was the use of change factors. And this involves using the relative changes from the climate models to update our historical baseline data, and allows us to link the output from relatively coarse resolution global climate models to our high resolution flood maps. We calculate the change factors for different global warming levels, which Nons has referred to earlier, to give us full flexibility in which emission scenarios and in which future time periods we can produce flood hazard data for. So as a simple example, if we look at the plot on the right-hand side, we can follow the red arrow vertically upwards to see that a global warming level of 2.5 degrees C results in a change factor of 1.5, which is equivalent to a 50% increase in the variable that we're interested in, which might be extreme precipitation, for example. And we calculate probabilistic change factors for each peril from ensembles of models where we can, rather than from single models, allowing us to estimate some of the uncertainty and confidence that we have associated with our future projections. Next slide, please. We'll now look at some changes, some examples of change factors for the different perils that we consider at Fathom. First, we have the pluvial change factors. So as Nons has mentioned, the Clausius-Clapeyron equation tells us that extreme precipitation is likely to increase as the climate warms. But rather than assuming that extreme rainfall increases everywhere at the same rate, we instead use an ensemble of 4 bias-corrected global climate models from the CMIP6 high-res MIP project to capture some of the spatial differences in these changes. On this map, the background colour represents the multi-model median of the change factors for extreme precipitation for a global warming level of 4 degrees Celsius. And the hatching on the plot shows areas with low model agreement on the sign of change. So if fewer than 3 of the 4 models project the same sign of change in precipitation, i.e. either an increase or a decrease, then we have lower confidence in the climate change projections in that region. As expected, extreme precipitation increases in most regions, with the average being approximately similar to Clausius-Clapeyron, but showing a fair amount of spatial variability. Only a limited number of areas are hatched, which indicated low confidence. So this ensemble of models generally agree on the sign of change over most land areas. Next slide, please. This is an example of a set of fluvial change factors from our global model, which were produced using an ensemble of 3 global hydrological models forced by 4 bias-corrected global climate models as part of the CMIP5 ISIMIP2B project. And the background colour represents the multi-model median of the change factors for river flow for a global warming level, again, of 4 degrees Celsius. And once again, the hatching on the plot shows areas with low model agreement on the sign of change, so fewer than 3/4 of the models projecting the same sign of change in flow. And whilst extreme precipitation is expected to increase in most regions, as we've discussed previously, the picture is not so simple for projected flooding. So you can see that the regions in green suggest an increase in flood peaks, but that some regions highlighted in brown are expected to have smaller flood peaks. And this is related to changes in different flood drivers in these regions, which Nils has mentioned previously, including soil moisture and snowpack. There's also more uncertainty in the projected flow changes, with a larger area shown to have lower confidence in the sign of change across the models than was seen for pluvial. Next slide, please. Finally, we have the coastal change factors. So these are based on the IPCC AR6 regional sea level projections, which are a synthesis of a series of models and emulators used to individually simulate the different drivers of sea level rise. The map shows the median absolute change in sea level for SSP 5.8.5 in the year 2100. And we can see that increased sea levels are projected almost everywhere, with some regions, such as around the Gulf of Mexico, showing particularly large increases related to oil and gas extraction and subsidence in these regions. There are also some limited areas which expect a decrease in sea level related to changes in land ice. Next slide, please. So to produce our global flood maps, each of these sets of change factors is used to update our historical baseline data to give us projections of flood hazard under different global warming levels. And this means we can produce inland and coastal climate conditioned flood hazard maps for a flexible range of future time periods, warming levels, and emission scenarios. And we believe that this is a really useful tool to help users to understand flood-related climate change impacts globally. Next slide, please. So we've talked about global scale flood modelling, but what if we're interested in future changes in flooding over a smaller region? It may be that global climate models aren't the most appropriate tool to use because coverage and physical consistency on a global scale may now be less important to us. Next slide, please. So climate models are really highly complex. They represent many different parts of the climate and Earth system. And as a result of this complexity, and particularly when run on a global scale, they require a huge amount of computing power and time. And this means, as Nans has mentioned, that they're often run at relatively low spatial and temporal resolutions, particularly when compared to the kinds of resolutions required for impact and risk modelling. But if we're interested in a smaller region, then climate data from regional climate models mentioned by Nans previously is available. So regional climate models are driven by output from global climate models, but because they cover a much smaller domain, they can be run at higher spatial and temporal resolutions. And this means that things like topography and its influence on precipitation and flood processes is better resolved compared to in global climate models, as demonstrated in the figures on the right-hand side of this slide. So here we can see the resolution of a typical global climate model on the top, which has grid boxes approximately 150 kilometers in size. Because the topography is averaged across the area of each grid box, there's not much variation between the grid boxes. Below that in the middle row is the topography of a regional climate model with grid boxes of around 25 kilometers. And you can see more of the spatial detail in topography starting to be resolved at this resolution. But at the bottom, there's the 30-meter resolution of our flood hazard maps, which includes much more spatial detail and smaller scale features. Other processes which are important for extreme rainfall in many regions, such as convection, are also parameterized in global climate models rather than being physically represented, as this would require spatial resolutions of a few kilometers. These very high resolutions aren't currently practical on a global scale, but on regional scales, these processes are starting to be physically represented in climate models. Next slide, please. So one example of a set of regional climate models is from the Cordex project, which is an international program aiming to better understand relevant regional and local scale climate phenomena, their variability and how they might change in the future through downscaling of climate data. Different regional downscaling models and techniques are used and evaluated, including dynamical downscaling using regional climate models, and then also statistical downscaling of global climate model data. And the current resolution of the downscale data as part of the Cordex project is 25 kilometers. And you can see some of the different model domains on the left-hand map, and then a close-up of the European domain on the right-hand map. So you can see a much smaller area is covered. Next slide, please. So the UK Met Office's 2018 UK Climate Projections, or UK CP18 data set, is another set of regional climate model projections for different emission scenarios. And these cover the UK and sometimes Europe at a range of different horizontal resolutions. A set known as the regional projections with a horizontal resolution of 12 kilometers we used in this paper that we're looking at here to explore uncertainties in the impacts of climate changes on high flows across Great Britain. In this paper, they used an ensemble of 12 regional climate model simulations with perturbed physics. So that means that each of the regional climate models was run with a slightly different set of physical parameters in order to assess climate model uncertainty. The bias-corrected climate data was then used to directly as input to the Decipher hydrological modelling framework across more than 300 catchments across Great Britain to produce flow projections for a historical baseline period of 1985 to 2010, and then a future time period of 2050 to 2075. And in the figures on the right-hand side of the slide, we can see the projected change in 3 indicators of peak flows for 3, which are in the columns, for 3 of the RCM hydrological model ensemble members, which are represented by the rows, selected because they show the highest, median and lowest Great Britain average change in Q10. So on the left-hand column, we have AMAX, which is the annual maximum flow. And then the middle and right columns are high flow quantiles, Q1 and Q10. So the flow value exceeded 1% and 10% of the time. And it's clear from these plots, or clear from many of them, that there's a kind of northwest southeast divide in these projections of peak flow, with many northerly and western regions seeing increasing flood peaks, whilst southern and eastern regions tend to see a decrease, particularly in southwest England, represented by red. And this drying in some southern regions is related to increased evaporation and the drier antecedent conditions that accompany this, leading to smaller flood peaks. And this figure and paper illustrates some of the uncertainties involved with modelling future flood changes. So in this example, only parameter uncertainty in the climate and hydrological models are considered, as well as which indicator for peak flow is used, shown by the different columns. And yet we can see that there are some quite significant differences spatially and also in the magnitude of projected change. Next slide, please. Another example of climate-adjusted flood modelling on a regional scale is Fathom's UK flood map. So for this, next slide, please. UK CP18 regional climate projections were again used, but here a change factor approach was used similar to that applied in our global model. UK CP18 climate data was used to calculate pluvial and fluvial change factors shown in the left and central maps for year 2070 and RCP 8.5. The pluvial change factors are positive in most areas, indicating increasing extreme rainfall, although in some regions, particularly along the northeastern coast of England and Scotland, there's a slight decrease or little change. And the spatial patterns of the fluvial change factors show more differences, as we've come to expect based on what we've discussed previously, with larger areas of drying projected along the eastern coast, likely related to the different flood drivers that we've discussed. Coastal climate change simulations incorporate sea level rise changes published in Kopp et al. 2014 and are shown on the right-hand map. And we can see that sea level rises everywhere, although by differing degrees. So there's larger increases along the southeastern coast of England and then smaller increases along the northwestern coast of Scotland, resulting from isostatic adjustment of the land in this area following the end of the last ice age, or the ending of the last ice age. Next slide, please. So one of the key uses of future flood hazard data is to assess how losses might change in the future due to changes in flooding. And as can be seen by the map in the bottom right-hand side of the slide, changes in expected annual damage in the UK due to a warming of 1.8 degrees C show significant spatial variation. So you can see evidence of some of the footprints from the different flood perils that are shown in the top plots in this map. And this is due to the complex interplay between changing flood drivers as well as changes in future exposure of assets. So we can see that areas of significant increases in expected annual damage of more than 25% compared to historical conditions are seen over the South East England, South and West Wales and Northwest England, whilst more modest increases occur over much of Central and Western Scotland. Meanwhile, smaller decreases in flood losses occur over Southwest, Central and Northeastern England. And results such as these have really important implications for both future climate action that may be taken and also flood adaptation in the UK. Next slide, please. And finally, we'll look at an example of more localised flood modelling, and this is provided by a research project that Fathom was involved in collaboration with the UK Met Office and the University of Bristol. Next slide, please. And for this, a convection permitting model developed by the Met Office was used. So this is a very high resolution with a resolution of 2.2 kilometres. And at this resolution, you can really start to physically represent some of the processes in the atmosphere, such as convection. And it means the model is able to resolve much smaller scale spatiotemporal features of rainfall and other processes, such as intense convective storms. And this is evident if we look at the maps on the right-hand side, which compare hourly rainfall for the same flood event from 1998. So whilst the larger scale features are very similar between the two, so we've got 12 kilometre data on the left-hand side and 2.2 kilometre data on the right-hand side, we can see in the 2.2 kilometre model on the right that you can, it's able to capture more local showers indicated by the top right arrow over the east coast of Scotland. The higher resolution also provides a more realistic representation of the rainfall, including areas of really high intensities, which are indicated by the bottom right arrow, which just aren't seen or captured in the 12-kilometre data. As part of this project, events were extracted from this climate data set and were routed through the ListFlood FP 2D hydraulic model covering the Bristol and Bath area to produce flood inundation. And it was found that the use of an event set from a convection permitting model results in greater inundation for the 30-year return period compared to flood changes derived from a regional climate model. And this is because more of the spatiotemporal features of rainfall, such as convection, are explicitly captured by convection permitting models. And as climate models and supercomputing capacity develops in the future, it's likely that there'll be a move towards developing these very high resolution models over larger areas and hopefully one day globally. Next slide, please. So just to finish off, we provide some references that we've used in this webinar in case anyone would like more information or to do any further reading. And I'll now hand back over to my colleague Gavin to discuss some of the ways in which large-scale flood model data can be used in industry. Thank you.
Great, thank you Natalie and Nans for providing a great walkthrough of the science that we use around climate. And I'll be putting that science into context with some real world examples in a minute. However, before we look at the use cases, next slide please, I wanted to really position where this broad scale flood modeling, flooding and climate data sits in the typical engineering project. This type of data really adds value to those initial stages for the analysis of most projects, where you're looking at sort of feasibility, prioritization or site selection, or you could be really looking at developing a really detailed evidence base for things like funding for future projects or the allocation of funding for particular responses to flood mitigation. So by using this data, it provides a much wider context and evidence for swifter, more informed decisions to help shape the strategic outcome for any project, for users to perform much more detailed flood modeling or climate adaptation analysis. So I'm going to look at several use cases today that highlight how our data can add value to some of the projects you may be involved in. So looking at now, next slide please. For site selection, we can look at two elements here. Firstly, there's that high-level screening where flood and climate risk scores can be used for estimating risk for all flood frequencies in a consistent output without the need to perform additional spatial analysis. So that's a very rapid screening process. But for more detailed analysis, the flood and climate hazard maps will give a much more in-depth review of each site, using all the three sub-perils together with both the defended and undefended views of fluvial and coastal flooding. And these data sets are used a lot by our clients and partners for a range of feasibility assessments. That can be data centers or renewable energy installations. As this data set is globally consistent, clusters of local, regional, national, or international sites can be analyzed and rapidly assessed in a uniform manner for both current and future climate scenarios to provide a range of future flood impact intensities. So solar farms are a great example of how Fathom flood data can really speed up this site assessment and selection process. In this example, we can see that the impact of fluvial flooding significantly compromises the suitability of the site based on the current solar array layout. It's therefore maybe more appropriate to redesign the array to accommodate fluvial flooding rather than condemning the site completely. So by using more detailed climate condition flood maps for this type of site assessment, alternative design options may emerge that weren't previously identified looking at the current climate state, and thus providing greater flexibility for the utilization of any site today and going forward in the future. Next slide, please. We understand that extreme flooding events we have recently experienced will become more business as usual under a changing climate. And so there's a critical need to enhance resilience to accommodate climate change, to raise the threshold of what we consider acceptable risk. By embedding future flooding consideration into the business planning and asset management processes, we will increase the resilience of our railways, highways, and many other linear assets that are distributed over wide areas, thereby reducing flood-related impacts in their construction, service delivery and operation, and maintenance. So using climate condition hazard maps to screen linear assets can easily and rapidly identify those wet spots, and with higher resolution, more definitive understanding of current and future flood risk across networks containing these assets, the delta between best case and worst case scenarios can really inform the decisions for resilience investment, prioritization, and subsequent adaptation. So critical assets, be they airports, data centers, or distribution hubs, are all susceptible to the impacts of natural hazards, as essentially all flooding is local. So for key assets, a more consistent flood assessment is required to understand the type and severity of the current and future flood risk. The very nature and behavior of pluvial, fluvial, and coastal flooding is different, and therefore it's important to understand how each subperil could impact the asset, both for the current climate state and for the operational lifetime of the asset. By using the flood hazard maps, it's not only the impact of flooding on the asset itself that can be qualified, but also the impact to the surrounding infrastructure that are connected to that particular asset. For example, vehicular access to a distribution centre or an airport. If the site is not impacted by flooding for a given intensity, it's also important to identify whether, for example, the main arterial routes into these sites are compromised, which could have a most significant impact on their operation. Next slide. So historic extreme weather events have highlighted the weaknesses and lack of joined-up understanding by central and local government, utilities, and other asset owners and managers of the widespread impact flooding events can have on critical infrastructure. And we know that these are only going to be amplified by both urbanisation and climate change. Climate condition maps are being used to underpin the understanding of current and future flood risk by CRADO, the Climate Resilience Demonstrator Project. Fathom maps are used as part of this project, which is linked into the Connected Places Catapult programme funded by the UK government. It's been set up to model and determine the spatial correlation and interconnectivity between discrete networks and their relative interdependency between assets to qualify infrastructure flood impacts caused by climate change in terms of disrupted customers or end users linked either directly to those flooded assets or customers disrupted indirectly due to network effects. For example, if the power supply is knocked out to a water treatment works because a local substation is flooded, many thousands of people will be directly impacted by a single point of failure with these critical interdependent assets. So it's really important to understand that connected relationship and also the impact of flooding both today and for future climate scenarios. Next slide, please. So building on the science that Nans and Natalie have just presented, we have developed the Climate Dynamics Framework, which provides ultimate flexibility for engineers and analysts involved in assessing flooding and climate hazard for their clients, as often these clients will require a variety of different climate scenarios, time horizons, and depending on the asset class, different reporting regimes or geography, and a range of other variables. So this framework is designed to accommodate the variability to meet the wide range of end users. And essentially it starts with the underlying global flood map, and then users can basically input their elements for their range of parameters, whether that's the particular climate scenarios, time horizons, or percentiles to get an understanding of uncertainty in the models. And the output is a climate conditioned flood map that's really going to inform a lot of decisions. And these maps are already being used for things like portfolio investment or asset acquisition purposes, as well as TCFD and other regulatory disclosures by our partners and customers to provide a greater insight on current and particularly future flood risk. This example is one of our partners, ERM, who are one of the largest global sustainability consultancies. And they've embedded Fathom climate condition flood hazard data into CRISP, their climate risks, impacts and solutions platform that combines a range of climate condition hazards to identify financial risks and opportunities that can inform organizations' plans as they transition to a low carbon economy. CRISP can rapidly assess individual sites and portfolios using a range of current and future climate-related scores to provide a clear perspective on the climate trends across a number of natural hazards which may impact an organization's assets. So that's the main part of the presentation, and we're going to be going now to our question and answer session. But before we get to the questions that you've submitted, I'd like to remind you to register for our next CIWEM webinar on the 21st of June. The link to register for the webinar will be in your chat panel shortly. We're also attending a number of events here in the UK, and so if you'd like to know more about who we are and what we do, please come up and say hello to us, and also find out the work that we do with CIWEM. Okay, let me turn to some of the questions that you've sent, and those questions that you have provided, and I'd encourage you to put more questions in the Q&A panel you can see at the bottom of your screen. Right, let's have a look at this. Okay, first question, and I think this is probably maybe to Nat or Nans, I'm not sure. It was mentioned that we use 4 climate models from CIWEM 6 in your global model. Can you give more information about how these were selected, please? I thought there were quite a few more models available. That's from Derek.
Thank you. Yeah, I can take that one. So, yeah, you're correct. In the wider CIWEM 6 ensemble, there's many more models, I think more than 50, I believe, from different institutions. The reason we selected 4, it was because we use a kind of sub-project from CIWEM 6 called High-Res MIP. So this was using higher resolution models than the wider ensemble of CIWEM 6 models represent. So I showed that figure where generally GCMs have a horizontal resolution of around 150 kilometers, but the high-res MIP subset of models have a horizontal resolution of 25 or 50 kilometers. So they're much higher spatial resolutions. And we believe they're kind of better at capturing some of the processes that are important for extreme rainfall and for flooding, and so because of that we decided to select those ones rather than the larger ensemble. Tropical cyclones are also obviously something that we are interested in, and you need a resolution of 50 kilometers or higher to really start to capture the processes important for tropical cyclones. So that's why we kind of went for a smaller subset of models, but one that we think better represent the types of climate variables that we're interested in.
Okay, thanks, Nat. Next question. This is from Naomi. For the coastal change factors, are they derived purely from predicted sea level rise at a given location, or is the surge component also adjusted for climate change, i.e. due to increased frequency, severity of windstorms? I think, Tom, this might be one for you.
Yeah, no, that's a really good question, Naomi. So for our coastal change factors, we just take into consideration the changes to mean sea level. There is an overwhelming body of literature on the subject that says that the changes to mean sea level are going to dominate the changes to return periods that we see into the future. There is a branch of research that is looking into how the changes to surge and tidal patterns will change with climate change. And that's something that we hope to integrate to our next version of our change factors. But at the moment, we just focus on the changes to mean sea level.
Okay, thank you, Tom. Next question, and this is from Tony. Why use different climate sources between fluvial, CMIP 6 and fluvial, CMIP 5? I don't know if that's Natalie or Nans can answer that.
Well, I can answer this.
Okay.
We wanted to use the best possible projections. And so for rainfall, the CMIP 6 high-res model are excellent because they're global and they run a fairly high resolution for GCM. So that's what we used. For fluvial, what we really wanted to not do is to use the output of GCMs. We wanted to use the output of hydrological models that have been calibrated to calibrate floods, to capture floods. But these models have not been used yet for a range of CMIP 6 climate models, but they have been used for CMIP 5 models. So that's what we use. We use simulation from EasyMIP 2B, so output from hydrological model driven by CMIP 5 models. And I've shown in one of my slides that the changes that we're expecting based on CMIP 5 and CMIP 6 are pretty similar.
Okay, thanks, Nans. Right, we've got another question. Well, this is a question from Alex. How will climate change be assessed, based on RCPs for tidal, fluvial and surface water risk in line with TCFD requirements? There is a disconnect between different climate models, e.g. return periods versus RCPs at varying time periods. I guess that's probably you, Nat.
Yeah, that's a good question. So in our global and in fact in our UK data set, we calculate these change factors and we assume that they are applicable across all return periods. So because of the model ensembles that we use, there is a relatively small number of models and then also a kind of 1 or 2 ensemble members, whereas to really start to assess changes in different return period events, you need much more climate model data. So you need a large ensemble of climate models that provides you with sort of many decades so that you can start to really look at changes in those kind of tail events. A lot of those ensembles, because of the computing time and power required for climate modelling, are therefore run at much lower spatial resolution. So you've kind of got this toss up between advantages of one method and then disadvantages of another. But yeah, so we assume that the change factors are applicable across all return periods, and then for different scenarios, the fact that we have associated those change factors with specific levels of global warming, it means that for the different scenarios, we would calculate at a particular time period of interest the degree of change in global mean temperature, so the degree of warming for that specific scenario, and then we would be able to calculate what the change in flood hazard would be. So it's really very flexible across different scenarios and different time periods.
Okay, thank you. And another question from Alex. Can you model wider natural hazards, physical risks, in which flood is only one of the TCFD climate indicators, or is this a future intention as part of your ESG offering?
Again, I can take that one. So at the minute, flood hazard is currently our main focus and our main area of expertise. However, we have recently partnered with RIASC, who are experts in atmospheric hazard models. So they develop tropical cyclone models specifically. So in the future, we'll be able to provide hazard data relating specifically to tropical cyclones. So that will include flood data and also wind hazard data as well.
Great, thank you. We've got another question here. For coastal flooding, what coastal topography data do you use? I guess that's one for you, Tom.
So for the coastal flooding, we simulate the inundation over our Fathom Plus product. So that's a DEM with forests and buildings removed that was developed specifically here with a team that was combined with Bristol Uni and Fathom. And that is also integrated with LiDAR, where there's LiDAR data available. So we sort of update it in those regions.
Okay, thank you. So this is from John. How is the maximum flow from a GCM defined? Is it the maximum discharge from a hydrobasin with some assumptions for, I assume, that local and perhaps antecedent conditions?
Yeah, I'll take this one. Thank you for the question. Yeah, so GCMs have include the land surface model. The land surface model will solve the terrestrial water balance. It will simulate soil moisture, antecedent condition. It will also simulate runoff. Some of the models will route the runoff and give actually flow in larger rivers. So this can be retrieved, like it was done in this Nature Climate Change paper, but it is not the approach we would recommend because GCM have not been created to simulate flow. Using hydrological models is the better way to do it, but it takes much more time and it's completely very intensive to do. The advantage of using directly GCM simulated runoff is that as soon as a GCM simulation is done, I mean, you can compute potential changes, and you don't have to wait for the hydrological models to be run. And what you get is a really rough estimate of how things are changing, but it's still probably better than assuming that clausus clapeyron is valid everywhere.
Okay, thank you. Another question from John. How do you take into account defences on the global flood scale? That's Tom, I guess.
Yeah, no, I can answer that. So obviously the DEM that we use to simulate flooding in most cases doesn't represent the defences. They're too small and too fine a resolution. In some cases in coastal stuff, if you have sort of really large natural defences such as dunes, they might be represented, but things like seawalls and sort of fluvial defences are too small. So what we do is we post-process the defences in. We identify the regions where there are defences or where we expect there to be defences, and we add that in. So we end up producing sort of two sets of maps. We have an undefended layer and a defended layer, and the defended layer will include those sort of post-processed defences.
Okay, thank you. And this is a question from Iftikhar. Apologies if I pronounced that incorrectly. When you say climate change, does it mean study of trends in temperature and precipitation only, or is it more than this?
So I guess it depends. I guess it's more than this. So the climate models represent not a fully complete view of the climate and Earth system. Obviously, you know, there are so many processes that it would just be impossible to represent everything, but they are kind of new processes that are being added every few years. But yeah, at the minute they do present a very complete view of the main drivers of climate change and the kind of main feedbacks that we think are important for this. And so we specifically extract changes in temperature and precipitation, but those are based on kind of modelling of the wider Earth system and all the kind of feedbacks and processes that go into that. So those are the kind of main variables that we take into account, but they are based on trends in other variables in the climate system in the background.
Okay, thank you. This one's from Ollie. Can I license the climate dynamics framework alone to plug into my non-flood risk models? I think it might be one for you, Nat, or I can pick that up. You can, yeah, and it's a case of using the data that we provide from the framework to support your other models that you may, other hazard or peril models that you may have. So I think that'll be relatively straightforward. So next question. The resolution of the AR6 sea level projections is quite coarse. Do you make any effort to downscale this data to use for the coastal change factors? I'm not quite sure who that's for, whether that's Nat or Nans or even Tom.
Yeah, I can answer that one. That's a really good question. So the sea level projections, you're right, they are quite coarse. They're at a 1 by 1 degree resolution. So we do make an effort to downscale them. We take in several ensemble members from the high-res MIP model runs, and they're at a resolution of 0.25 degrees for the ocean. So we basically we contrast the subcell deviation from that high-res MIP the mean sea level variable out of those model runs, and we then take that expectation and use it to downscale the AR6 mean sea level projections into the future.
Okay, great. Thanks, Tom. We've got time for one last question, and it's from Fan. My question is about the bias correction part. Can you please share more details about the bias correction methods? What I'm aware of is that we can correct the historical data towards the observational records and apply the same algorithm to the future data. Are there any other details or standards in terms of bias correction?
Yeah, I can take that one. That's a really good question as well. So a much more kind of in detailed description of how we bias correct our global data is included in the climate dynamics webinar, launch webinar that I mentioned earlier. I think the link to which is in the chat, but briefly, you're right, we did only and can only really bias correct to historical records. It's true that the biases in the future and to different climate forcings may not be the same as those seen in the historical period, but it's obviously very difficult to try and work out how those biases might change. And so for the climate data that we used for the pluvial and the fluvial change factors, we bias corrected using the ISIMIP methodologies. So the fluvial ones were using a kind of previous iteration, ISIMIP 2B, and then that was the fluvial, sorry, the pluvial were ISIMIP 3. And the ISIMIP methodology provides a framework for bias adjustment and then also statistical downscaling of climate model data. So it aims to reduce the biases, but it aims to preserve the original climate signal, which is obviously what we're interested in if we're looking at climate change. So yeah, we bias adjust that data, and we do assume that the biases in the future will be the same as in the present day. Yeah.
Wonderful, thanks, Nat. Well, I'm just conscious of the time, and I'd like to thank you for your great questions. Unfortunately, there's a few more we have not been able to answer because we're running out of time. But we will follow up with those questions, and we will be providing links to the webinar in a follow-up email and links to the previous webinars we've done, and the link to the next webinar on the 21st of June, looking at compound flood risks and extreme events. Thank you very much for your time, and I look forward to speaking to you on the 21st. Thank you. Goodbye.